Good morning. In this video, I'm to introduce equilibrium constants with weak acids and bases. We're going to focus on how to calculate Ka and Kb for weak acids and weak bases, and how to find the pH of a solution that contains weak acids and weak bases. Before today, I will deal with our strong acids and bases, which are quite straightforward. All you need to do is to do pH equals negative log of H3O plus concentration. But here we're going to look at weak acids and bases, which involves the use of a RICE table. So the first type, we're going to look at two types of examples. First type is determining K from initial concentrations and measured pH. So here I have a 0.10 molar aqueous solution of lactic acid, and that's a weak acid. And I'm given with the initial concentration that's 0.10 that has a pH of 2.43. What is the value of Ka for the lactic acid? So I'm trying to find the Ka value. So what I do here is that I write, first step is to write out the reaction in an aqueous solution. Usually that step is given though. So I have the lactic acid, which is right here, reacting with water in an aqueous solution to produce. So since this is a weak acid, I have its conjugate base, which is after removing a hydrogen proton, it becomes CH3CHOHCO2. This part is the same as that. All I have removed is a hydrogen plus, so that gives me a 1 minus charge, and an H3O plus, or hydronium ion. So then I'm going to write my equilibrium expression. So because water is a liquid, I don't consider water. So I have the two products in my numerator, and I have the reactant, which is the lactic acid, in my product. And then I'm going to convert pH to H3O plus. So because H3O plus concentration can be deduced, so what I can do is that I can do 2.43 equals negative log of H3O plus. Using your skill and learning in the last lesson, you can actually find the concentration of H3O plus to be 3.7 times 10 to the negative third power. If you forgot how to do that, I recommend you to go back to the last video. And now I have this equilibrium expression. I have the concentration of H3O plus. I can then proceed. I'm going to put a standard RICE table. Note that here we call it the ICE table, but this is really the reaction instead of equilibrium. I have this equilibrium expression, and I have initial change and equilibrium. So in the initial state, my concentration for lactic acid is 0.10, but initially I don't have any product. So I'm going to write 0.10 and 0, right? All I have is initial. Water is not considered because it's a pure liquid. For change, remember that for any change, plus or minus, we only consider the stoichiometric coefficients. Here the coefficient is 1, coefficient is 1, coefficient is 1. Reactants are being consumed and products are being created. So the reactants are always negative and the products are always positive. So you have to change. If you're still paying attention at this moment, email Mr. Chen why the reactant is negative. And for equilibrium, you're going to just sum up the first and second row. So in this case, it will be 0 plus x, 0 plus x, 0.1 minus x. It's my equilibrium column. Now, what I can see here is that the two axes are going to be the same. So I can effectively conclude that hydronium concentration and my conjugate base concentration, or those two, are going to be the same. And before this, in my last step, I found that my hydronium concentration is that. So I can conclude that they're both equal to 3.7 times 10 to the negative third power. And now I can then use my Ka formula. In my Ka formula, I have the two products, but note that in my reactant, I have this 0.1 minus 3.7 times 10 to the negative third power term in my reactant here. And by putting all those into a calculator, you can find the Ka of this weak acid. So now your turn. A solution is prepared from 0.55 moles of butonic acid dissolved in sufficient water to give 1.0 liter of solution that has a pH of 2.72. You are to determine the Ka of butonic acid. The acid ionizes according to the balanced equation below. So in this case, what I'm going to do is I'm going to do Ka. So you need to do a RICE table for this problem. So I suggest first of all, you start by writing an equilibrium expression for Ka. Again, you ignore the water. And secondly, so you can do that first. And secondly, you can find the H3O plus concentration because the pH is given. So you can find the H3O plus concentration from the given pH. And third, you're going to do a RICE table of the initial change and equilibrium. Here, the initial, you're given, you have 0.055 moles of butonic acid in 1 liter. So the concentration for butonic acid is really just 0.5055 moles over liters over 1 liter. Okay, and then you can get a initial concentration of butonic acid. And then you have no products initially, and you know the change from the balanced equation, which right now is already balanced. And then your product, in your equilibrium, you can just add initial and change. And you can do the RICE table, and then you're going to plug in the numbers to find the Ka value. Use the example that we just did for guidance. The second type of example we're going to look at is to calculate the equilibrium concentration and pH from Ka. So here you're asked to calculate the pH of a 0.020 molar solution of benzoic acid if Ka is 6.3 times 10 to the fifth power for the acid. So you have Ka, you have concentration. Here you are trying to calculate the pH. So what should you do? In this case, the equations given. Equations are usually or almost always given. So you don't usually need to worry about writing equations, but the first step is to, it seems like here I can start with my RICE table. So whenever you see a weak acid, when you have a long formula like that, the chances are it's a weak acid. So you're going to write the RICE table. So in the initial state, I know the concentration of benzoic acid, which is 0.020. Do I have any products? No. How about water? Water is a liquid, so therefore water is not considered. So I just have 0.020 and no products at all. So when I go to change is only related to the stoichiometric coefficients. 1, 1, 1. So pretty easy in this case. Reactants are always negative. Products are always positive because products are produced and reactants are consumed. And for equilibrium, Beverly, no. Okay, and for equilibrium, I'm gonna do initial plus change. So here 0 plus x, initial plus change, 0 plus x. Initial plus change, 0.020 plus negative x, which is 0.020 minus x. And I have this change column. Sorry, I have this equilibrium constant. And then according to the stoichiometry, I know that H3O plus concentration is equal to C6H5CO2 concentration, which is X at equilibrium. I can then have my equilibrium expression, products over reactants. And here I know my Ka, which is the equilibrium constant for the acid, which is written right here. Let's substitute that Ka here, which gets me 6.3 times 10 to the negative fifth power, which is equal to, now in my numerator, both are x's, so x times x, over, in my denominator, I have the equilibrium here, which is 0.020 minus x. And then what I can do is that, remember back in module 4, module 5, I can ignore the minus x part in my denominator. So all I have left is 6.3 times 10 to the negative 5th power is equal to x times x, which is x squared. Don't tell me 2x, over 0.020. And then to solve for x squared, you multiply those two together, or you multiply both sides by 0.020, and then you take the square root. I just skipped a step. So all you need to do is to do the Ka times 0.020, put it under square root, which gives you 0.0011. If going from here to here, the math is challenging for you, let me know outside of class time. So now I know the x, which is, what is my x? My x is H3O plus. My x is also C6H5CO2 minus. So I can say that the concentration of those two is 0.0011 molar. Okay, do I need to find the concentration of C6H5CO2H? I don't, because the question never asked, but I can by doing 0.020 minus x, which is given here. Finally, I can go back to my questions as to calculate the pH. So how do I calculate pH? I have my H3O plus concentration here. So what I can do is say pH equals negative log of H3O plus concentration. I'm going to put that here. That gets me 2.96. And this is an example of how you can calculate the pH of a weak acid. Note that whenever you have a weak acid or a weak base, you must do a RICE table. You cannot just plug that into negative log equation. All right, your turn. What are the equilibrium concentrations of acetic acid, the acetic ion, and H3O plus for a 0.1 molar solution of acetic acid with the Ka that's given? What is the pH of that solution? That question looks a little intimidating at first, but let's look at that. So you have acetic acid, which is CH3COOH. That's aqueous, reacting with water. In equilibrium, since this is a weak acid, we are in equilibrium with my two products. So first of all, this is an acid. I want to find a conjugate base. Remember, if I remove a hydrogen, and usually it's either, or usually it's a standalone hydrogen. So I'm going to take the one in the end. Usually on the AP exam though, this will be given. So I have the conjugate base for the acetic acid, plus hydronium, H3O plus. And it seems like it's balanced as it is. So now you have the equation. You just need to do a RICE table. You have the initial concentration, you have Ka, and then you're going to find the pH of the solution and find the equilibrium concentrations. That's the end of this video. Make sure you do both problems, and you're going to check for those on Monday.